Hello, my name is Wesley Upshur and this is my lab partner Dylan Davis. We are senior mechanical engineers at Tennessee Technological University. This presentation is meant to highlight much of what we have learned in our dynamic modeling controls class, its application, and some of the interesting information we researched for our case study on the topic of gun tube projectile dynamics. Gun tube projectile dynamics is the process of examining a projectile and developing the barrel mechanisms necessary to equip it with specific initial conditions. The projectile is a bullet in this case, and the bullet will only spend a few milliseconds in the barrel. It's within this small window that the projectile trajectory is determined. Once the bullet leaves the barrel, gravity and air resistance are the only forces affecting its motion. With our understanding of the kinematic equations, we can easily predict a bullet's behavior once it is airborne. Based on the caliber of the bullet, its velocity on impact, and the rigidity of the target, we can hypothesize this outcome as well. Gun tube projectile dynamics considers all three of these systems, working backwards from the desired outcome to develop initial conditions to ensure it. For demonstrational purposes, these processes have been divided into three systems. System 1 is when the bullet is in the barrel and can be modeled as a mass spring system. System 2 is when the bullet is airborne and can be modeled as a projectile. Finally, System 3 is upon impact. We model this system using ballistics, which is beyond the scope of this course. Once the intended purpose of the firearm is determined, these are the steps taken to design the weapon. Geometric idealization is the dimensional analysis of the system. Governing equations is the theoretical analysis of the system. Interface models are the internal components in relation to another. Gun system modeling is how the operator interacts with the system. Numerical solutions are the theoretical behaviors based on different inputs. The final result is reviewing all these steps. With the end result in mind, we begin with geometric idealization. For example, ammunition caliber is selected based on the intended target's toughness. Once ammunition type has been selected, the corresponding barrel is chosen. The range a weapon is intended for will determine the barrel length and the gas that will propel the bullet. Within the ammunition casing is powder that will be ignited, causing gas to rapidly expand within the gun's barrel, propelling the bullet towards the exit. The bullet will accelerate within the gun's barrel up to the gas's maximum expansion point. If the bullet is still within the gun's barrel after the maximum expansion point, it will begin to decelerate due to the damping kinetic friction, now exceeding the gas pressure. The maximum expansion point will determine the barrel strength required to safely house the bullet's ignition. To maximize performance, the barrel length will exactly correlate to the gas's maximum expansion point, while maintaining the length required to accurately engage the target within the weapon's designated range. The angular velocity required to stabilize the bullet during flight is based on the bullet's geometry and inertia. The tighter the rifling angle, the greater the angular acceleration to the bullet, increasing the initial velocity exiting the barrel. By the end of the geometric idealization, all these factors have been considered and the best possible ratio achieved. Following geometric idealization, the governing equations must be derived. Our system, at a minimum, must include the gas peak pressure. This will provide us with the driving force for System 1, the mass of the bullet, its kinetic friction to determine the frictional damping force, and for detailed models, the atmospheric pressure of the environment that the weapon will be used at will need to be included as well. Once the equations of motion of the bullet are determined, from these we can calculate the initial conditions for System 2. We know that once the bullet exits the weapon's barrel, it will behave as a projectile. By solving System 1's equation of motion, we have the initial velocity of System 2. With this velocity, we can calculate the bullet's flight time, derive its effective range relative to bullet drop, and predict its velocity upon impact. This is where our design process started, upon impact. We chose the ammunition type first because if we had completed all the preceding steps and the projectile would not arrive with the necessary precision and kinetic energy to be effective, we wasted our time by engaging in a trial and error type method. This is why you work backwards from your desired outcome. The interface model step considers how components interact with each other and creates the mechanisms for them to do so. When the weapon is fired, much of the expanding pressure is recycled and rerouted to drive the bolt backwards, discharging the empty casing and compressing a spring that will in turn push the bolt forward, reloading the next round into the chamber. This allows the weapon to fire semi and automatically without the operator having to use a bolt action mechanism.
The gun system model is comprised of the components that the weapon operator interacts with. Ergonomics is immensely considered when engineering a weapon with this complexity. As previously stated, much of the reaction force of the expanding gas is used to drive a bolt back and is absorbed by the spring that pushes the bolt forward to reload the gun. However, the recoil force is not entirely negated and is translated through the buttstock into the operator's shoulder and arms. Another phenomenon we must consider is the muzzle climb, which refers to a weapon's tendency to increase its muzzle elevation caused by compounded recoils following successive firing. This decreases weapon accuracy. Muzzle climb can be reduced by leveraging the operator's strength and additional weapon attachments. The pistol grip is angled toward the operator so that their hand's normal force is directed toward the ground, which redirects the muzzle back to its initial firing position. The addition of a vertical and sometimes angled foregrip further assists the operator's efforts to counteract the muzzle climb. The buttstock is padded and contains a spring to reduce the jerk the weapon exerts on the operator. Additional attachments can be added for user comfort, increased performance, and personalization purposes. For the numerical solution method, the governing equation and the kinematic equations will be solved. We learned several techniques in class for solving these types of equations. You could write a program to vary different variables independently, then graph the results, and easily identify the combination of variables as needed. Once the theoretical solution suggests that your weapon system will perform favorably, you would then run ballistics simulations with your data. These simulations allow for high-volume testing in various conditions instantaneously and will give an estimate of a weapon's prototype performance. Finally, with all your equations solved, you can present your data of the weapon system. All this data can be generated using computer programs or by hand if you wanted to devote enough time. This is some mock data of the Colt AR-15 with different ammunition types. The reason some of the different colored lines are dropping quicker than others is due to the size of the bullets. For example, a full metal jacket bullet will weigh more, thus having greater inertia, which would require a greater angular velocity to maintain stability during flight. However, the bullet twist is determined by the barrel's rifling and the maximum pressure point. All other variables held constant, a heavier bullet would rotate slower, reducing effective range, decrease accuracy, and would even increase the jerk on a weapon's operator. The majority of companies will use a similar design analysis process in order to reduce the cost of their research and development projects. Even with simulation techniques such as this, in 2019, the Congressional Budget Office estimated a total spending of over $30 billion dedicated to weapon development. They predict the number will be above $60 billion by the year 2028. These numbers do not include private spending, but are sufficient in showing the enormous amounts of resources that are being devoted to producing state-of-the-art and next-generation weapon systems. In dynamics modeling controls, we have learned not only how to create the systems necessary to solve these advanced problems, but have already practiced many of these techniques as well. We have been trained in different software languages, data collection methods, and how to simplify complex systems into a simple mass spring system. We wrote MATLAB codes that work in tandem with LabVIEW and Simulink to solve multiple degrees of freedom state space models. Much of our learning built upon existing knowledge from classes such as physics, dynamics, mechanical engineering analysis, and dynamics of machinery. Even though weapon development is not our concentration, it is pretty cool to know how our class experience relates to various other fields. Articles and data references can be noted below. References for all pictures can be noted below.